Also he made a molten sea of 10 cubits from brim to brim, round in compass, and 5 cubits the height thereof. And a line of 30 cubits did compass it round about. 10 cubits across and 30 cubits around. So that extract from the Old Testament gives pi the approximate value 3. But much earlier the Babylonians used this value, which is 3.125. And the Egyptians used this value, which is about 3.16. The Hindus used root 10, which is also about 3.16. Now we saw in an earlier program that Archimedes estimated pi by approximating a circle with regular polygons. That was in 250 BC. Using polygons with 96 sides, he showed that pi lies between these values. And this gives pi to 2 decimal places, 3.14. By taking polygons with more sides, one can get better estimates. Around 500 AD, the Chinese found this approximation, which gives pi to 6 decimal places. And this approximation wasn't rediscovered in Europe until 1,000 years later. Well, for hundreds of years, the geometric methods were the standard way of calculating pi. In 1593, pi was found to 15 decimal places using a polygon with 2 to the power 30 sides. That's over 1,000 million sides. In 1610, pi was calculated to 35 decimal places. And in fact, the man who did the calculation spent most of his life working on the problem, and the approximation was engraved on his tombstone. And around the same time, a polygon approach led to this first formula for pi. It's an infinite product involving more and more square roots. So that's the geometric approach. But around the 17th century, with the development of calculus, new formulas arose for pi. One formula involving products was discovered by the English mathematician John Wallis. It's basically the formula you met in the integration unit. But unfortunately, this formula is not very good for calculating pi because it converges far too slowly. A better approach was discovered by Gregory and Leibniz in the 1670s, and it involved representing functions by power series.
To see what was involved in this new approach, look at this right-angled triangle. As you can see, tan pi by 4 is 1. And so, pi by 4 is tan to the minus 1 of 1. Or pi is 4 tan to the minus 1 of 1. But how do we calculate this? It turns out that we can represent the function tan to the minus 1 of x by a power series, which is called the Taylor series of the function. And one way of finding the Taylor series of a function is by calculating the Taylor polynomials of the function. For example, let's take a function like this and try to approximate it near 0 by polynomials. A constant function is a very poor approximation. A linear function is better. We've given it the same slope at 0 as the original function. With a quadratic, we can make the second derivatives agree as well. Indeed, you can see that as we take higher and higher degree polynomials, then we get better and better approximations to the function. So, let's see what these approximations are. This is the formula for the Taylor polynomial at 0 of degree n, Tn of x. Let's see where this formula comes from. We want Tn to have the same value as the function when x equals 0. And it does so because when x equals 0, all these terms involving x's just vanish. We're left with f of 0. We also want Tn to have the same derivative as f at 0. Well, look what happens when we differentiate. The constant term vanishes. The term with f dash 0 loses its x, but the remaining terms still contain x's. So, when x is 0, we're just left with f dash of 0. And the same thing happens when we match the second derivatives. So look at the second derivative of Tn. The first term is now f double dash of 0. The remaining terms still contain x's, so when x is 0, we just get f double dash of 0. And the same thing happens for higher derivatives. All the derivatives of Tn at 0 up to the nth derivative have the same values as the corresponding derivatives of f have at 0. So what are the Taylor polynomials for the function tan to the minus 1 of x?
To find the Taylor polynomial of degree n at 0, we need to evaluate the function f and its first n derivatives at the point 0. So let's try to do this with f of x equals tan to the minus 1x. If we substitute x equals 0, we just get f of 0 equals 0. Well, now for the derivative of tan to the minus 1x. That's 1 over 1 plus x squared. That's one of the standard derivatives. And if we substitute x equals 0, we get f dashed of 0 equals 1. And that means that the Taylor polynomial t1 of x is just equal to x. Well, next we differentiate again using the composition rule. The derivative of 1 over x is minus 1 over x squared. So the derivative of 1 over 1 plus x squared is minus 1 over 1 plus x squared all squared times the derivative of 1 plus x squared, which is 2x. And now if we substitute x equals 0, we get f double dashed of 0 is equal to 0. And that means that t2 of x is the same as t1 of x. Well now, to find t3 of x, we're going to need to differentiate again. Well, f double dashed of x is a quotient, so we need to use the quotient rule. First, there's a minus sign, and then in the denominator, we get 1 plus x squared all to the 4th. And then in the numerator, we have 1 plus x squared squared times 2, which is the derivative of 2x, minus 2x times the derivative of 1 plus x squared all squared. And that's 2 into 1 plus x squared times 2x, using the composition rule again. Well, we can cancel a 1 plus x squared. And now if we simplify everything, what we get is this. Minus 2 plus 6x squared all over 1 plus x squared all cubed. And now, if we substitute x equals 0, we get f treble dashed of 0 is equal to minus 2. And that means that t3 of x is equal to x minus x cubed over 3. We get minus 1 over 3 here because it's minus 2 over 3 factorial. Now, to get the next term, we'd have to differentiate minus 2 plus 6x squared over 1 plus x squared all cubed. And I'd rather not do that. Later terms would be even harder to work out. So, finding the Taylor polynomials of tan to the minus 1x directly seems to be rather difficult. But remember, our aim is to find the Taylor series of tan to the minus 1x. Is there some other way to do it? Well, for this function, there's a special trick we can use. The derivative of tan to the minus 1x is 1 over 1 plus x squared. And that's the sum of the geometric series which has first term 1 and common ratio minus x squared. So it's 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Now, how does that help us to find the Taylor series for tan to the minus 1x? Well, if we integrate the left side, we get tan to the minus 1x. So that suggests that if we integrate this power series term by term, then the power series we get might be the Taylor series for tan to the minus 1x. Well, integrating term by term, this is what we get. 1 gives us x, and then we've got minus x cubed over 3, plus x to the 5th, over 5, minus x to the 7th over 7, and so on. But remember, what we wanted was a way to calculate good estimates for tan to the minus 1, 1, pi by 4. So can we substitute x equals 1 into this formula to get pi by 4 equals 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, and so on. Certainly this series is convergent by the alternating test, but is its sum equal to pi by 4? Let's look at a computer program which calculates the partial sums of this series. In the display, we've multiplied these partial sums by 4. Do they converge to pi?
Now, while Phil's waiting for his computer, let's go back and see how we can justify the techniques he used. So what did he do? He took the power series for 1 over 1 plus x squared and integrated it term by term to get the power series for tan to the minus 1 of x. And then he substituted x equals 1. Well, first, are we allowed to integrate a power series term by term? Yes, we can do it, but only under certain conditions. And to understand these conditions, we must first say what we mean by the radius of convergence of a power series. For each power series like this, there's a number r called the radius of convergence. If mod x is less than r, then the series converges. And if mod x is greater than r, then the series diverges. That means that the power series converges at all points in some interval centered at 0. And at all points outside this interval of convergence, the power series diverges. But what happens at the endpoints minus r and plus r? In general, we just don't know. If we want to find out about convergence here, then we've got to look at the series itself. For example, this geometric series converges if mod x is less than 1, and diverges if mod x is greater than 1. So its radius of convergence is 1. Actually, this series diverges when x equals minus 1 or plus 1. Now, one thing I should mention is that we haven't actually said just what values this number r can take. Well, it can be any positive real number, or it can be 0. There are power series which converge only when x is 0, or it could be infinity. Of course, that doesn't mean there's a real number infinity. It's just another way of saying that the power series converges for every value of x. Now, Phil integrated this series term by term, and that is valid so long as we stay inside the interval of convergence. In general, the series we get by integrating a power series term by term has the same radius of convergence as the original series. And the function it defines is a primitive of the original function. So by the integration rule, we can integrate our series for 1 over 1 plus x squared term by term to get from the left-hand side tan to the minus 1 of x, and from the right-hand side x minus x cubed over 3 plus x to the 5th over 5, and so on. Both sides vanish at 0, so I don't need to put in a constant of integration. Now, all that's valid when mod x is less than 1. But unfortunately, it doesn't tell you what happens when x equals plus or minus 1. And what Phil did was to substitute x equals 1. Now, you might think that that would not be valid, because the original geometric series doesn't converge when x equals 1. But rather surprisingly, the integrated series does converge when x equals 1, and its sum is pi by 4. But that's rather hard to prove, and I won't go through it now. So let's see how Phil's computer is getting on with calculating pi using Gregory's series.
Not very well, I'm afraid. We've added up nearly 2,000 terms, And we've only got 2 decimal places correct.
So, although this series converges, it converges very slowly. We can use Gregory's series for tan to the minus 1 of x, but if we want it to converge faster, then we'll have to use a smaller value of x, smaller than 1.
This approach, still using Gregory's series, was taken by Abraham Sharp in 1699. If we look at this triangle, instead of the one we had before, then tan of pi by 6 is just 1 over root 3. So that pi by 6 is tan to the minus 1 of 1 over root 3. Now if you put 1 over root 3 into the series, then it converges a little faster. And in fact, Sharp used this method to calculate pi to 71 decimal places. But a much better method is to use the addition formula for tan to the minus 1, which appeared earlier in the course. The formula is tan to the minus 1 of x plus tan to the minus 1 of y is tan to the minus 1 of this expression, x plus y over 1 minus xy. If we put x equals a half and y equals a third, then the expression in brackets is a half plus a third over 1 minus a sixth, which is 1. So what does that give us? Well, we get tan to the minus 1 a half plus tan to the minus 1 a third equals tan to the minus 1 of 1, and that's pi by 4. So this gives us another formula for pi. And as we'll show you, we can use the tan to the minus 1 series to approximate each of these terms on the left. But there's an even better formula called Machin's formula, after John Machin, who used it in 1706. Pi by 4 equals 4 tan to the minus 1 of a fifth minus tan to the minus 1 of 1 over 239. That last term looks rather odd. Where does the 1 over 239 come from? Well, it's a bit complicated to derive, but you can check it like this. If you take tan to the minus 1 of 1, which is pi by 4, and add on tan to the minus 1 of 1 over 239, then the addition formula gives you this, tan to the minus 1, 120 over 119, and that's just twice of tan to the minus 1, 5/12. And that's 4 times tan to the minus 1, a fifth. That's using the addition formula twice. So pi by 4 plus tan to the minus 1 of 1239 is 4 times tan to the minus 1, a fifth. And that's just Machin's formula. And the tan to the minus 1 series for this formula converges much faster than the ones we've had before. In fact, Machin himself used this formula to calculate pi to 100 decimal places. And in 1873, using the same formula, William Shanks calculated pi correctly to 527 decimal places. For a long time, this remained the most prodigious piece of calculation ever performed.
Now let's look at those last 2 formulas for pi by 4 and use them to estimate pi. Here's the first, tan to the minus 1 a half plus tan to the minus 1 a third. Each of these numbers, a half and a third, is less than 1. So we can certainly use the Taylor series for tan to the minus 1x, with x equals a half and x equals a third. Here's the Taylor series for tan to the minus 1 a half. And then we add on to that the Taylor series for tan to the minus 1 a third. Now, we can add the terms of these 2 series to get a single series for pi by 4. A half plus a third, then these 2 terms give this, and so on. We can do that by the sum rule for convergent series. So that's how this formula gives a series for pi by 4. But in the same way, we can use this equation, Machin's formula, to obtain another series for pi by 4 by adding together the corresponding terms of these 2 series. We've written a computer program to calculate the partial sums of the series obtained from these 2 formulas. And we've multiplied by 4. Let's see how quickly each of them approximates pi. Here are the successive partial sums. As you can see, the second series gives pi correct to 8 decimal places more quickly than the first, and they were both far quicker than the original series I used. But why is that? Well, roughly speaking, the speed of convergence of the series for tan to the minus 1x depends on the size of x. The smaller x is, the faster the series converges. So the speed of convergence of this series is determined by a half, whereas the speed of convergence of this series is determined by 1/5, which is much smaller. So we can do even better by obtaining formulas for pi by 4 which involve inverse tangents of even smaller numbers. Here's one such formula. It's more complicated than the ones we've just looked at, but the speed of convergence is determined by this number, 1/8. And so it's much faster than these.
So using different tan to the minus 1 formulas, we can get better and better estimates for pi. And once computers started to be used for calculations, the number of known digits increased rapidly. In 1961, Machin's formula gave 20,000 digits. And in 1974, that 1/8 formula gave 1,000,000 digits. Since then, methods have been discovered with even faster convergence, and pi is now known to about 16 million decimal places. But let's finish with a couple of novelties. In 1897, the state of Indiana decided to legislate a value for pi. As it happened, the wrong value. The bill was referred to the House Committee on Swamplands and passed its first reading unanimously. But luckily, a mathematics teacher appeared on the scene and the bill was shelved indefinitely. And finally, how many digits of pi can you remember? Well, there are several mnemonics which can be used for remembering them, and the word lengths give the successive digits. For example, may I have a large container of coffee? But this one is really my favorite. How I want a drink. Alcoholic, of course. After all those formulas involving tangent functions.